Time dilation? What? Hello YouTube, this is Daryl Lim, and I'm going to be talking to you about time dilation. I'm going to be using the two postulates of relativity and implement the train experiment. Let's get started. The first postulate of relativity states that the speed of light is constant for all reference frames. All reference frames basically means that the velocity of the observer and the source are constant. The speed of light is about 300 million meters per second. Okay, it's 299,792,458 meters per second. But for all practical purposes, we can go ahead and round up to 300 million meters per second. Now let's say that I am on a stationary platform shining a light to a friend a distance d apart. He sees the light after t naught seconds. So the velocity of light, c, is equal to the distance that the light traveled divided by t naught seconds that it took to get to him. Now let's say I'm on a high-speed skateboard going at him really fast. I shine a light at him a distance d away from him, and it takes t naught seconds to get there. The speed of light is still going to be measured as c, regardless of my extra speed toward him. The second postulate of relativity states that the laws of physics are the same for all reference frames of constant velocity. One law of physics is velocity is equal to distance divided by time. That means that the velocity of an object equals to how much distance it covers divided by how much time it takes to get there. Let's say I throw a ball a distance d away, and it takes t naught time to get there. The velocity of the ball can be said to be the distance that it traveled divided by the time it took to cover that distance. Now let's just say that this experiment is now in a high moving train. It has flames coming out the back. The train's going really fast. If I do that same experiment, I shoot a ball a distance d away and it takes t naught time to get there. The velocity of the ball relative to that fast moving train is still going to be d over t naught. The law of velocity still applies regardless of the speed of the reference frame. Now if I'm on a train that's accelerating, which means it's changing its velocity, then the law of velocity equaling to distance over time does not apply anymore. Okay, let's get on to the train experiment now. Let's say that I'm on a really big train. It has a height of 150 million meters. So there's me, small, with a laser on the bottom, and there's a mirror on the ceiling. Now if I shine a laser, I'm going to go ahead and make myself blue. If I shine a laser up and have it come back down after reflecting off of a mirror, it will take 1 second to reach me. That's because the speed of light is 300 million meters per second and the train's height is 150 million meters per second, half of that. So if it goes both up and down on the train, it will be traveling 300 million meters, and it would have to take 1 second to do that. There's an observer outside the train. Let's call him Red. He is stationary relative to the train, and let's say the train is moving 200 million meters per second. That's about 2/3 the speed of light. So that's really fast. Now, he's not going to see the light go up and down because the train's moving while the light is traveling to the mirror and back down to the observer in the train. So he's going to see the light instead move at a diagonal up towards this now moved mirror and back down to the now moved observer in the train. So that other blue person to the right of the first blue person is the same person after the train has moved so much amount of time when the light travels back down. So let's go ahead and complete this triangle. And what he's going to see is a new length L that the light has traveled each way. The length L is going to be the hypotenuse of this right triangle that we have built. The right triangle is going to have one leg of 150 million meters, which is the height of the train, and 100 million meters, which is half of the distance that the train traveled during this experiment. If you take the hypotenuse, L is going to be 180,300,000 meters. Now, Red is going to see light travel 2L, which is 360,600,000 meters. That's going to be called red T. Now, blue is going to see light travel, as mentioned before, only 300 million meters. We'll call that blue T. Both observers agree to see the same thing. That is light traveling from the blue observer up to the mirror and back down to the blue observer. Now let's go ahead and solve for time using the two postulates of relativity. As stated before, the distance that the red observer sees the light travel is 360,600,000 meters. The distance the blue person sees light travel is only 300 million meters. The first postulate of relativity states that c, which is 300 million meters per second, is going to be the same for all observers. So red and blue can agree that c is 300 million meters per second regardless. Now, we're going to use that equation c is equal to t over little t. Now that's basically the same as that equation we used for the second postulate of relativity, which is velocity is equal to distance over time, except the velocity is the speed of light, the distance is capital T, and the time is little t as always. Now let's go ahead and solve the equation. For blue, c is going to be 300 million meters per second, and that's going to equal to the distance traveled, which is 300 million meters divided by time. Solving for t, it's going to be 1 second as stated earlier. Now for red, the speed of light is still 300 million meters per second, and it's going to equal to the distance traveled for him, which is 360,600,000 meters. And we're going to go ahead and divide that by t. Now solving for t, actually we're going to get 1.2 seconds. Now that is time dilation for you. Both observers, using the two postulates of relativity, agree that light speed has to be 300 million meters per second. But the distance traveled for the same event is different, so the time has to have been different as well.